My coffee machine is very simple. It has a power button that turns green when the boiler is ready and a lever switch with 3 positions. Left for cold water, center to stop the flow, and right for hot water. In this video, I'm going to integrate it into Home Assistant to control it remotely and add my own custom controls, each with an adjustable timer so the machine automatically stops based on the cup size I choose. So let's disassemble it. Inside we have the boiler that heats the water pump, and on the other side, the control board, which also supplies power to all the components. I hope it's obvious, but I will say it anyway. During all of this, the power cord must not be plugged into the wall. The board is protected by a plastic cover that also holds the rubber power button. Now let's disconnect the cables and remove the control board from its plastic cover. Here are all the connectors: live, neutral, pump neutral, boiler neutral, lever switch, cap holder sensor, boiler temperature sensor, and on the back of the board is the power button. Same as in my last project, I'm using the ESP32C3 Super Mini, which comes with a Wi-Fi antenna and 2 headers. Since on this ESP the antenna connector isn't actually connected, we need to bridge these tiny pads together with a bit of solder. For this, I'm using my new soldering iron, sent to me by Veneercy. This is the HS02B model, which is great for microscoping soldering like the one I'm about to do, because it uses C210 tips. To trigger the power button and the valve switch, I'm using this Optocoupler module. To trigger the Optocoupler, we just need to run one wire from in1 to one of the ESP pins and another wire from G to the ESP ground. After that, we clean both sides with isopropyl alcohol. Alright, let's connect the black wire to ground and the white wire to in1. Now we plug the ESP into the computer and open ESPHome Builder in Home Assistant. We will add a new device, give it a name, pick the board and click install. Once it finishes, we download the project and open ESPHome Web. Click connect, pick your ESP from the list and install the project we just downloaded. After that, if we go back to Home Assistant, the device shows up online and we can add new code. The output tells the ESP that pin 1 is controlling the white wire and the switch section creates a switch in Home Assistant called power, which turns the Optocoupler on or off, like in this example. Here I have a button similar to the one on our control board. Using this code would hold the button pressed, but that's not what we want. As you saw at the beginning, the coffee machine button expects a single tap, so let's change the code. Now it will press the button, wait 100 milliseconds and then release it, like in this example. Let's save and install the code. To find the button pin's polarity, we can set the multimeter to DC mode and touch the pins with the probes. If the reading is negative, we just swap the probes until the negative sign disappears. This way, the multimeter shows us the correct polarity. Red is always positive and black is always negative or ground. Because the button pins have continuity, we can solder the wires either on the bottom side or on the top side. Next, we reconnect the board to the coffee machine. The blue wire we just soldered goes to the Optocoupler's ground, and the grey wire goes to the Optocoupler's V1 connector. At this point, we can connect the ESP to the computer. Before powering the coffee machine, we can see that if the red jumpers are connected, the ESP ground has continuity with the coffee machine ground. After we remove the first jumper, the ground connections are isolated and we can plug the power cord into the wall socket. The multimeter shows a positive value, which means the wires are connected correctly, and we can finally test the power button. The power button works, so let's check the valve lever switch. But first, if you try something similar, keep in mind that shorting 2 pins by mistake can fry your device, and touching the board while it's powered can be dangerous. If you are okay with that, let's continue. Make sure the device is powered, and with the multimeter in DC mode, we measure the lever switch joints, black probe on ground and red probe on each joint, one by one. When the lever is in the off position, we only read 3.6 volts on the middle joint, so on the black wire. With the lever in the hot position, we read 3.6 volts on the black and the red wire. And with the lever in the cold position, we read 3.6 volts on the black and the blue wire. So the lever basically connects the black wire, which always has 3.6 volts, to one of the colored wires, blue for cold water and red for hot water. Since we are going to use 2 more optocouplers from the module, we need to remove the jumpers from those channels. We are going to connect the black wire to V2 and V3 at the same time by bridging them. And on the ground side, we will connect the red and blue wires. Let's start by connecting these 2 points together. We cut the lever switch connector and we will need 5 jumper wires. 3 of them will be used to extend the connector wires, and the other 2 will be soldered to the ESP to control the optocouplers. Cut the pins, strip all the wires, and use soldering sleeves to extend the connector wires. Because later we will also need wires that goes to the lever switch, strip and extend those as well using another 3 jumper wires. Next, solder the orange wire to ESP pin 2 and the yellow wire to pin 3. Now we have 1 wire for each optocoupler, plus 1 for ground. So we have power, hot and cold water and the ground wire. On the other side, we have the grey and blue wires going to the button, and the 3 wires connected to the lever switch connector. We connect the lever connector to the control board, then reconnect all the other coffee machine wires and sensors, except for the wires to the lever switch, which we'll use later. Power up the ESP and let's switch back to the code. This sets up 2 switches, hot on GPIO2 and cold on GPIO3. Only one can be on at a time thanks to the interlock, and both starts off when the device boots. This creates a valve selector with 3 options, off, cold and hot. Choosing one turns on the right valve and turns the other off. These commands are not really needed because the valves already have interlock, but I added them anyway just as an extra safety step. Save and install the new code to the ESP and let's test it. As you saw, I tested it without the water tank to avoid spilling water on the components, but this actually hid the problem I was worried about. I will explain it a bit later. Now it's time to solder the lever switch wires to the ESP. Black to 3.3 volts, blue to pin 5 and red to pin 6. At boot, I saw the ESP pin 1 and pin 2 are high for a small interval which triggers the optocoupler. I knew about pin 2 but not about pin 1, and after a small research I saw that during boot switches are set to their initial value. We know our switches are off by default, so at boot the power switch is set to off, which triggers this code. To fix this, we can modify the code to run only if the switch is on. We set all switches restore mode to always off and create 3 binary sensors, one for each lever position. ESP reads cold and hot lever state using GPIO5 for cold and GPIO6 for hot, and the lever off state is read using a template that checks if the cold and hot lever are off. When these sensors are triggered, they set the valve mode selector to the corresponding state. We set these sensors to internal and create a text sensor to display the lever state position in Home Assistant. Another way of doing this is to create a simple text sensor which gets the state when the lever has moved. To keep the coffee machine synced with Home Assistant, we set the valve mode to off whenever the device is turned on or off. Now let's save and install the code. The valve follows the lever state, but the command is not reaching the optocoupler. The reason for this is set action, which only runs when the select is changed manually. Changing it to on value makes the code run whenever the select gets a new value, so it properly triggers the optocoupler. Now, on boot, Optocoupler 1 isn't triggered anymore. For Optocoupler 2, there is nothing we can do because this is how the ESP32 works on boot. After a closer look to the lever switch, I realized this coffee machine has two tubes. One for hot water and one for cold water. When you move the lever to cold, it physically blocks the hot water, and when you move it to hot, it blocks the cold water. Since this project took a lot of time and I had no idea how to simulate the lever's physical movement without ordering new things, I decided it wasn't a big deal. To manually control the coffee machine, we'll use 3 buttons, which means more cables. At this point I realized soldering the wires wasn't a great idea, because during testing and recording I had to move things around a lot, and some cables broke, so I grabbed another ESP, soldered pin headers, and replaced the cables. I won't show the whole process, but I will explain everything you need to know. As before, we have ground and pins 1, 2 and 3 that controls the optocoupler. Brown goes to ground, white to pin 1, orange to pin 2 and yellow to pin 3. The only difference here is that I also connected the brown wire to ground because we'll need it later. On the optocoupler side, nothing changed, all the wires stays the same. I tied all the red wires from the buttons together and they need to go to 3.3 volts pin. Since the black wire from the lever switch also needs 3.3 volts, I soldered them together along with 2 extra red wires. Jumper wire goes to the ESP 3.3 volts pin and the other one will be used later. The blue wire from the lever goes to pin 5 and the red one goes to pin 6. We connect the red wire, the one that's tied together with the button's wires and the lever's black wire, to the ESP 3.3 volts pin. I also extended the button wires with jumper wires matching their colors. Blue goes to pin 4, yellow to pin 7 and red to pin 10. Reconnect everything to the control board. Power the ESP and the coffee machine and let's add new code. This code creates 3 number controls for the blue, yellow and red buttons. Each lets you set a time between 1 and 60 seconds and they remember the last value even after reboot. This creates a sensor that tells us when the script is running, and this is the script. It runs when the button is pressed. It takes the button color as a parameter to know which timer to use. If another script is already running, it turns the valve off and stops. Otherwise, it sets the valve based on the lever position, cold or hot, waits for the time assigned to the button, then turns the valve off again. This line handles the delay for each button based on its color. I spent a lot of time making this work. I wrote it in one line because I couldn't find a way to split it into multiple lines that worked. To detect the button's press, we create 3 binary sensors. Blue is on GPIO 4, yellow on GPIO 7 and red on GPIO 10. When any button is pressed, it stores the button color as a parameter. If the script is already running, changes the parameter to off. Then it runs a script. Since we'll be controlling the coffee machine with the buttons from now on, let's change the lever code so it no longer triggers the valve when it's moved. On boot, we update the lever state and set the script running state to false. Let's install the code and see how it works. If we move the lever to the off position, pressing the buttons does nothing. If we move it to hot and set the yellow button timer to 3 seconds, pressing yellow will trigger the hot valve for 3 seconds. Red set to 1 second keeps the valve on for 1 second. If for example blue is set to 30 seconds and we want to stop the coffee machine earlier, pressing any button will stop it. Next, we make 3 holes for the buttons, clean up the mess and mount the buttons. To check the device state, we'll use a TMT6000 light sensor. For ground and VCC, we'll use the brown and red wires, and we'll need another wire for out. It will read the power LED, which is right under the power button. I first checked the exact position, marked it with a pen, and then made a hole in the case so the sensor could see the LED. Now it's time to solder the wires to the sensor. The red wire goes to the ESP 3.3V pin, the brown wire goes to ground, and the purple wire goes to GPIO 0. We reconnect the cables for the last time. Back to the code, we create a new binary sensor for the device state, which will be visible in Home Assistant. To modify its state, we will be using the light sensor. In simple words, the light sensor transforms light into voltage. When the voltage is higher than this value, device state is changed to on. When the voltage goes below this value, device state is changed to off. These values can be different in your case. In my case, they look like this when the device was off. After turning on the device, the values increased a bit and state changed to on. And after turning it off, the values decreased and state changed to off. Now we cut the live and neutral wires. We strip the ends, connect ferrules to wires that goes to the components, plug them into a wire connector, we connect an additional wire to the live wire and crimp it with a ferrule. We do the same for the neutral wire. Connect the ferrules to the wire connector, so now the power wires are connected again. We connect ferrules also to the additional wires, which we will use to power the ESP. This time we'll use a USB power module, which is like a phone charger. On the back it has a 2-wire connector where we can plug the additional wires. We plug a USB cable into the USB module and use it to power the ESP. I moved the USB module wires on top of the power cable to hold it in place. The optocoupler will be held between this bottom plate boss and the edge of the case. I applied isolation tape to the pump hoses to protect them from the sharp edges of the ESP and place the hoses in their holder. So this is the result. Now, if we want to use the coffee machine manually, we turn it on, open the capsule slot, and place a coffee capsule inside. We wait for the power button to become green, set the lever to the hot position, and press the blue button. For this coffee cup, my wife told me that the blue button, which is set to 30 seconds, is perfect. In a moment, you'll see what perfect means for her. And this is what my wife considers perfect. This can be fixed very easily from Home Assistant, where I created a special button that when pressed opens the settings menu that allows changing the time of each button. So let's lower the blue button to 23 seconds and press it. For a larger coffee mug, we can increase the time of another button. If we press a button either manually or from Home Assistant while the lever is in the off position, the coffee machine will not start. The lever needs to be moved to the hot or cold position to enable the buttons. When child lock is on, the buttons are disabled. Turning it off restores button functionality. This modification of the coffee machine also allows the valves to be turned on while the lever is in the off position. This mixes hot and cold water, resulting in warm water, which was not possible before. The coffee machine can also be controlled from the main control, which has 3 colored sub-buttons, one for each button. There is also a dedicated button for the child lock, and the last one is the power button, which turns the device on or off. The state updates after 1-2 seconds because of the way we configured the light sensor filter, which helps us avoid false positives. And that's it. If you like this video, you know what to do. Thank you for being here, and I will see you in the next one.